Hi there, Jeff Rideout from Memorial University, continuing our series on Matlab Essentials. In this video, I'd like to introduce you to M files, which is how we write and execute programs in Matlab. I'm going to bring in the document, the folder link for which is in the description below. Starting on page 6, I'm going to introduce programming with the aid of a simple example that anyone who's done high school physics will remember. It's the projectile motion equations. You can pause the video at any time and look at the screen, read the description, or just pause and look at the document if you've downloaded it. Projectile motion problems are constant acceleration. Some of the well-known equations are if y is the displacement above the ground, positive upward, y is the initial y naught. So we're going to imagine throwing a projectile off, say, the top of a building. Y naught plus the initial velocity v naught times time plus a half acceleration times time squared, where in this case acceleration would be minus 9.81 meters per second squared downward. So negative 9.81 or negative 1g. The velocity is whatever the initial velocity v naught is, plus at, and again a is negative, so the velocity will decrease as the projectile reaches its peak height and then starts falling down. Alright, so let's write an M file to plot y versus time to introduce basic programming functions. We need to open up a new script. So on the top left of my screen here, I click on New Script, and an editor popped up on my other screen, which I'll bring into the frame here. Your Matlab, when it opens, it may show the editor as being docked in the same sort of environment as the command window. Okay. If you want more space for both your command window and your editor, you can click on this little triangle and you can undock. Now we can work in a bigger white space here. So what do we want to do here? Well, if you've been doing a lot of Matlab stuff and you've got a lot of variables built up in memory, or if you have plot windows open, it's not a bad habit to begin your program with close all and clear all. Clear all clears all existing variables from memory so they don't interfere with what you're trying to do in your current program. Close all will close any plot windows that are open. If you want to add a comment, but you may not want to, but you should, if you want your program to be sort of decipherable by others, or maybe even by you when you come back to it after a long time and say, what was I doing here? The percent symbol, it'll turn the line green, and you can comment your files accordingly. All right. So in this example, let's say I want to begin with an initial projectile height of 10. I'm just going to declare the variable y naught equals 10. Right? I don't need to allocate any space in memory. I just type it in. Initial height's 10 meters. When you run the program, Matlab would spit out y naught equals 10 at line 5 once it came to it, because as you may recall from the first video, if I type in y naught equals 10 and hit enter, it spits it back on the screen for me. Your programs will typically run faster if you suppress output that you don't want. If I put a semicolon after the 10, I don't get any screen output. If I come back to my command window and type y naught equals 10 semicolon, right, I don't get that screen output. So y naught is 10. I'll define the initial velocity. I can put the comments after the command if I want. I can throw the percent symbol in wherever I want. V naught, let's say this thing is going upward with an initial velocity of 5 meters per second. And I'll put in the acceleration minus 9.81. Now, I don't want to just know what y is for one point. I want to go forward in time a whole bunch of points starting at time 0, and maybe I want to run this simulation of the projectile height until the projectile reaches the ground. Alright, so I'll start off at time 0 with y equal to y naught, and I'll run it forward in time until y goes to 0. So my point is, I want to maybe take 100 time points. We'll say n equals 100, number of time points. Now, let's say I want to have time going from, let's say, 0 to 10 seconds. And let's say I want to divide that 10-second interval up into 100 time points. And I want them to be equally spaced. There's a command called linspace, which will linearly space your points. I want points linearly spaced from 0 to 10. How many points do I want? I want 100 of them. Excuse me. So this command will go generate a time vector going from 0 seconds to 10 seconds with 100 equally spaced intervals, 100 equally spaced time points. If you select a little block of your M file and right-click on it, well, you can copy it, or you can even evaluate this selection in the command window. So if I wanted to see what that command t equals linspace does, I can just right-click, evaluate the selection in the command window. Oh, it didn't recognize the variable n. Okay, so I'll put in here. Actually, what I'll do is I'll go back here, and I will select n equals 100 and the linspace line. Right-click and evaluate the selection. Okay. I don't see anything because of the semicolon, but if I type t, I have 100 columns of time points going from 0 to 10 seconds, and it's in a row vector. If I wanted to transpose that row vector and make it a column vector, t prime, right? Prime is the standard linear algebra symbol for transposition. T prime, there it is. All right, so back to regularly scheduled programming. If I can get back to my editor. All right, so I've got my time points. Now, at every time point, I want to calculate y, and I want to calculate velocity. I want to loop through 100 time points. So I do a for loop. For I equals 1 colon n. In different programming languages will have slightly different syntax for the for loop. In Matlab, the colon takes you from 1 to n. You don't type 1 to n. You type 1 colon n. So 100 times, I am going to do the following. I am going to first work out the displacement. Y is equal to, I'm just going to enter in the equation, y naught plus v naught times t plus a half, 0.5, times the acceleration times the time squared. All right. Now, there's a problem with this. I want to do this 100 times. I want to generate 100 different values of y, one for each time point. So I need to use an array index here. Okay. If I just loop through this, and you can see it does some smart indenting too, which is kind of nice. If I just run this now, it's going to calculate y 100 times, but it's not going to store them in an array. I'm going to end up with only one value of y at the end, that being the final value. I'm also going to get an error because t is a vector of 100 points. When I equals 1, I want to use value 1 from the time array. So I always want to pick out just the ith value of the time vector. Put that in. So now every time I loop through, I'll pick the next value from the time vector. I want to log y and add a new value to the y array after each time step as well. So I want the ith value of y to be dependent on the ith value of t. Y naught, v naught, and a are constants. They don't need to change or update, so I can keep those like that. Now if I want to put in the velocity, I want to find the ith value of v at whatever time point I'm using. It's going to be equal to v naught plus a times the ith value of t. Okay. All right, well, that's fine for now. That should, by the time this loops through, I should have a 100 element time vector, a 100 element position vector, and a 100 element velocity vector. I'm going to save my file now. I'm going to save it as. And I'll just call it something proj for projectile. And it will automatically be given an M file extension for an M file. Suppose I want to run my file. Well, I could do this in a few ways. I could select everything, I suppose, and I could right-click and I could evaluate the selection in the command window. I could press this big green play button to run it, or I could go back to my command window and I could simply type the name of the file, proj. If I don't remember what files are in my directory, I can do ls. I could do ls star.m to find out only the M files, and I see proj is in there. It's case sensitive now, so I got to type capital Proj. Don't need the .m. Hit enter. All right. Nothing happened because all my screen output was suppressed. But now in my memory, I've got v and y, which are 1 by 100 double precision variables, and t. So y, there it is. Turns out that after my 10 seconds, it's 430 meters below the ground, and it started out 10 meters above the ground. And somewhere in the middle of this y array, I can see where it hit the ground, somewhere around column 21 or 22, which means that the time for it to hit the ground was around 2 seconds. Of course, you're probably going to want to plot this. So let's talk about plot commands. So put in a comment, plot results. You can either just type the plot command, plot t, comma y. As long as those vectors are the same length, it should do that. Just try that from the command window, plot t, comma y. It will automatically open a new figure, and it'll set the axes automatically. All right, so I can see I start at 10. I can zoom in on the plot if I want. Right. So there's a little magnification button there. Zoom in, and I can see that the zero crossing when it hits the ground is at about 2 seconds. So there's a number of things I can do with the plot here. I won't go into them in detail in this video, but I can edit the plot window, figured properties. Right, there's a dialog box that should open here, which will let me set up things like the axis scaling and whatnot. I just closed it prematurely. So all the figure editing, if you poke through that on your own, it's pretty intuitive. If I want to put this in my M file, as you saw when I typed the plot command, it opened a new figure automatically. If you want a specific figure number to open, I can type figure 1, plot t, comma y. If I want to put an x-axis label on there, there's an x-label command, round parenthesis, and I put a vector, a string actually, in single quotes. So this is the string that'll show up on the x-axis. I can do a similar thing for the y label. I can put in y of t, put in the units in meters, and put that in a single quote. All right, and I can put a title on there. So again, these are things you can do in the edit figure properties dialog box, but I'll just do them here in a sort of old school way. Displacement versus time. And the final thing that I'll do is I'll put some limits on the axes. Well, actually, let me just run this first to make sure I've got it all correct. So I'll press the green run key this time. Here's my displacement versus time curve now with a title and axis labels. If I only wanted to plot the first, say, 2.5 seconds on the x-axis, I could do x limits. Now, round parentheses. I'm going to put in a range of times going from, say, 0 to 2.5. So similar to how we define vector variables, I need a square bracket in which I put the vector 0, 2.5 indicating the extents of the time axis. That goes in a round parenthesis. If you do help xlim, if you forget whether it's a round bracket or a square bracket, help xlim will tell you. And I can do some y limits as well in case I don't care about the part of the simulation where it's already gone down below ground. So I got some x limits and some y limits. Run this again. It closes my figure, reopens it, and now I've got some sensible, or in my case, more meaningful axis labels. You can put a couple of different curves on a single plot using the subplot command. So subplot. If I want to have 2 rows of plots and 1 column of plots, I can say 2 by 1. Subplot 2 by 1 will give me a 2 by 1 array of plots on the same figure. And then the first of those plots will be the top one. So 2, 1, 1. That's going to stack the plots in a 2 row by 1 column arrangement. I can do plot t, y. And then I can do subplot. I'm going to work in the same 2 by 1 figure, but now this is going to be plot number 2, so it'll stack that one below, plot t, v. All right, we'll run that, see what happens. Okay, so going back to the program here, figure 1 opened figure 1 and plotted t, y. Then when I went down and I just went into my subplot, it overwrote figure 1. So first figure 1 was plotted with all those fancy labels. I should have declared a second figure, figure 2 there. Now it'll keep my old plot and it'll give me this new one. So here's what I mean by that 2 by 1 stack of plots. The first one is the displacement, the second one is the velocity. What I'm going to do now is I'm going to load in one of the files I've already prepared. It's a fancy version of this, and you can get it from the folder, the link to which is in the description below this video. So I'm going to open a script now. I'm going to go to my Open button, and I'm going to open up, I called it yplot when I did it before. Okay, so there's a new tab in my editor window, and it's got a lot more comments. It's got the same stuff that we just had, and it's got some plotting. I've got labels on the first and second figures. I've also put in a few other options here. In this plot command down here, it plots t, v, and then there's a number of options you can have for things like line type and line color. So in my single quotes here, I put R:, so that's going to give me a dotted line in red, as opposed to the default, which is the blue line. So if I run this version of the file, oops, I seem to have an error. Okay, let me just go back here. This is interesting. I got an error. I heard the bling of doom from my speakers. I'm not sure if it came through on the computer. Okay, so I go back to my command window. One thing about Matlab that's really nice is you get super intuitive most of the time error messages. Unrecognized function or variable v in this new fancy, supposedly upgraded version of the plotting file that I just opened. It tells me there's an error in my freshly loaded yplot file on line 45. It tells me the specific line, and it says that it can't recognize the variable v. So let me go back here and see what I messed up. If I click on this error message, it'll take me right to line 45. So it can't find v. So let me see here. Did I not put v? No, okay, I didn't even put it in there. Okay. So vi equals vo plus a times ti. All right. Put that in there. One of the other things I was going to point out too is you can do matrix manipulation, and you can store matrix variables within the for loop. So I'm looping through here, and 100 times I'm spitting out a y and a v value, writing them to an array. If I wanted an output vector, so if I wanted my output vector at each time point to consist of vector, square bracket, if I wanted to write y and v, okay, so now what I'm looking for is a 2 by 100 output vector. I got to be careful here on how I index this. If I just go, the first value of the output vector is yi, vi, it's going to say there's a dimension mismatch here. Out brackets I suggests a sort of a 1 by n array. I want a two-dimensional array. So I think what I want here is I want y and v to be the first row of my output vector. So I want 1 comma I to be yi, and I want 2 comma I to be vi. So I need to do something like this. I need to say for the output variable I'm defining, everything comma I is the corresponding y and corresponding v value. Try that. So I run this again. Now I get two plots. Okay, the y plot is black because down here I used single quotes k. K gives me a black line. And you can find all these different letter codes corresponding to the line colors. And as I said down below, the R colon, the R was the line color, and the colon gave me the dotted line. And now if I type out, I do have my 2 by 100 variable, the first row of which, let's see, 1 comma everything. That gives me the position. And the second column, sorry, the second row, so 2 comma everything. That gives me the velocity. Okay. I think that's all I want to say right now about the plotting functions. Okay? So the programming, again, I think it's pretty straightforward. You just type your commands in a logical way according to the syntax into the M file. You save it, you execute it from here, or you execute it from the command line. The error messages are intuitive, and when you click on them, it'll take you right to the part of the program where there's an error. And in the next video, I'm going to talk about saving the data, doing interpolation, some post-processing of the data you may generate with your M files.